Hi, and welcome to this lecture. Today is the topic is on magnetism, and the lab. I'm sorry, the lecture notes are actually on Canvas. So we're going to go through basically that, and I think I prepared a demo for you guys for a motor. I can get that to work. I have batteries to connect it to it, and that uses basically the same the principle of magnetic induction in a wire. No, actually not the magnetic. How magnetism is created actually in a wire. That's exactly an electromagnet, okay? At some point, let me plug this thing in here. At some point, there will be a current running through this wires, which is at the bottom. It's just these two connections. So, and that will induce a magnetic field inside these coils. And that magnetic field will interact with this permanent magnet and create a permanent motion, which is really the principle of a motor. So that's basically what we'll be doing. What is this battery? Because I need to radiate. And they have several batteries. All of them are 1.5 volt, just to make sure that we're ready for that. Anyway, so let's get into the topic. Okay. So let me share. So we're looking at chapter 24, as I said, and this deals with magnetism. Magnetism fascinated mankind from the first time when it was discovered. And of course, it's still kind of something that is of interest to us in science because it has so many things in here. Magnets appear in two forms. This is a permanent magnet, and it's actually color-coded. You have the north in red and the south in blue. This is also a horseshoe magnet. Again, if I change it, on one side you have the red, which is the South Pole, and the North Pole on the other side. And which one is south, which one is north is actually a matter of convention. As a matter of fact, I have a bunch of magnets in here. Put them all at once. All of these are magnets, okay? And I still have some more, okay? Some far more magnets in here. So these are permanent magnets. These are what is known as permanent magnets, as opposed to electromagnets. The one I was talking to you earlier about was actually an electromagnet. It has magnetism only when there is electricity, which begs the question is, what is magnetism? So we'll try to understand, to talk about that. So we'll talk about the magnetic force. We'll talk about the magnetic poles. I already mentioned the fact that we have a North Pole and a South Pole. The fact that we call them North Pole and South Pole will just be related to the fact that when we have a compass, it points to the north geographical pole. So we called magnets as basically having two directions, a North Pole and a South Pole. Something you need to know is that the north geographical north is actually the magnetic south of the Earth, because the needle, which has a north, points to the south. Anyway, so magnets, they come in two flavors. They come in a North Pole and a South Pole, and you cannot separate the two. That is one thing that is, no matter what you do, you cannot have a North Pole by itself and a South Pole by itself. They always come in pairs. So if in case you start with a North Pole and a South Pole, and you decide, you know what, I really want to isolate my North Pole and South Pole. So what you do in this case, you come up to this region and you cut the magnet, and you will have this end of it. And of course, you will have the second end of it. So what happened in this case, where you made the cut, this side would be south, this side would be north, and this would be south. So basically what you end up with is two permanent magnets. So you decide, you know what, I'm not too happy. I mean, for some reason, I just came into this region and split it halfway. So how about if I split this one halfway? Well, the process repeats, that's all. So you'll have north-south. You divide this one, north-south, and so on and so forth. So the question is, what happened when you keep on doing this until at some point, you're going to, there is no more divisions? Do you think we will be able to isolate the North Pole from the South Pole if we continue through this process? Because at some point we'll be on the atomic level. So what happened then?
the atoms themselves are still polarized.
Okay. And if we split those two? Can we, here is my question, can we have a North Pole by itself and a South Pole by itself?
No, right? Because eventually you only have one particle.
Okay. So actually you're right. Okay. Technically we cannot have a North Pole by itself and a South Pole by itself in this sense. In the sense that it is an individual poles by themselves floating, like charges, for example. If I take this thing in here and rub it against the cat, I don't have a cat right now, but if we have a cat or a dog, you will see that it will have charges. How do I know that? It can induce a charge in a piece of paper and it can lift it. So this, you can isolate charges. As a matter of fact, the charges are the ones that are moving in electricity. So with charges, you can isolate them. And you can have a negative charge by itself and a positive charge by itself. You just carry it wherever you want to, and now you have a positive charge or a negative charge, whichever you want to. However, for magnets, they seem you cannot have monopoles. So the goal in here is to have a monopole. Okay, it seems like this one do not exist. Monopoles do not exist as far as we can tell. That is really the as far as we know. In this sense, okay? And there are some theories out there speculating about their existence and trying to modify things, especially on the cosmic level, and that maybe they existed in the beginning or something, because there is something weird about the symmetry between charges and magnetism, except now for some reason, that symmetry is broken when it comes to this behavior, okay? Now, on a solid state level, apparently there is a new research out there that you can basically somehow have separate poles, okay, where you can treat each and every one of them as an individual pole. And that is fascinating because it can lead to some interesting studies related to the properties of materials. Anyway, for all we know right now is that there are no monopoles. So if you continue with this process, at some point you're going to destroy the magnet. At some point you're not going to have any magnets. So just before the destruction, you still have a North Pole and South Pole by itself. But just that step where you're about to basically go into a North Pole by itself and South Pole by itself, you end up with nothing. You lose the magnet completely. Both of them are gone. So that's basically what the behavior is. Okay. We'll try to understand what permanent magnets are using this concept of magnetic domains. So what's happening on the atomic level, actually, each atom is made up, of course, of a nucleus and the electrons orbiting it. So the electrons, they pair their spins together and they cancel their motion, basically. So each electron has a property called the spin. It's like a rotation around its own axis, if you wish. But just that's an analogy that is not exactly correct. So you have to be very careful with this one. So spin property cancels for most of the inner electrons because they pair. Okay, and when they do, they cancel their magnetic properties. The outer ones, though, they appear, at least some of them are not paired, and those that will have their spin definitely oriented in a specific direction. And the spin is what gives rise to magnetism. That is the main thing. Also, on the nucleus itself, again, the protons and the neutrons, both of them have spins. They also pair with each other. As a matter of fact, the helium atom, which has 4 nucleons, has 2 protons and 2 neutrons. So it appears to be a very well-balanced nucleus because all the spins cancel each other inside the nucleus. And because the nucleus also contributes to the spin, albeit it's a small quantity, because a huge mass that it has compared to the electrons that have a very small mass, then they contribute the most. So the electrons is the main contributor when it comes to the magnetic properties. However, this is not the entire picture. the fact that the electrons are in motion around the nucleus behaves as if it's a current also. So there is an orbital contribution to the magnetism. So there are actually all kinds of contribution to magnetism, and magnetic behavior is really related to all of the statistical behavior of all of this phenomena. On average, it cancels out. However, in some materials, like for example, iron, nickel, and cobalt, you will have regions of space where this random motion will exist in such a way that there is a definite orientation for the entire magnetization of that region. This region this way, there is another region next to it like this, there is another region next to it like this. On average, these are called domains. On average, everything cancels and you don't have magnetism, unless you take that material and put it in a magnetic field already from a different magnet, then they will orient themselves. More or less, the different domains will have a net region. This one this way, that one this way, this one probably this way. But in all, on average, they have a net magnetization that is pointing a specific direction. And now you have a permanent magnet. So basically, when you lift the magnetic field that caused this, or the effect that caused that one, because it doesn't have to really be necessarily a magnetic field. Now, I mean, the easiest way and the most basically industrial way is through magnets to magnetize them, and they're electromagnets, not permanent magnets. They, after you lift that magnetic field, the external magnetic field, they retain their magnetization in that region. How do they do that? By something called a self-consistent solution. This domain relies on the one next to it to stay aligned in this direction. While the other domain relies on, so basically here are two domains next to one another. This one is relying on this one to stay oriented in this one, in this direction. This one relies on its neighbor to stay oriented in the same direction. So both of them are leaning on one another, basically. And this is only for some materials that have this property called ferromagnetism. Other materials, they lose magnetism the minute you cancel it. Like, for example, even iron has properties that are paramagnetic properties, and also they have diamagnetic properties. So materials, they actually orient completely in the opposite direction, okay? Again, this depends on the structure of the material and what property picks up from the material. So again, magnetic domains explain the behavior of materials when it comes to magnets. So it's this motion of the charges in these regions, in addition to their internal quantum behavior, that gives you magnetism. So that is what a permanent magnet is. The electromagnet is easy. As long as you have charges moving, then it's magnetism. You kill the current, the electromagnet dies. The advantage of an electromagnet, though, is that you can achieve tremendous amounts of magnetism with it versus a permanent magnet. Permanent magnet, you cannot do a lot. It reaches a point of saturation. So when you're trying to build magnetism in it, there is a point you cannot magnetize it anymore. It's useful for recording devices, it's useful for other things, but not for anything more than that. So again, electromagnets are used now in MMRs, for example, in the hospitals, they're used in laboratories, they're used when magnetism, for example, for levitation of trains, actually, they lift trains with it. And that is because you can achieve tremendous amounts of magnetism with it. So all you have to do is just yank the current up, that's all. As long as you can increase the value of the current and keep the system cool, because with the higher and higher currents, there is Joule heating. The material starts to heat so much. If you can keep the temperature low enough, so you can achieve tremendous amounts of magnetism of the order of a Tesla or 10 Tesla or even 20 Teslas. Because magnetism usually is a very, very tiny quantity of the order of a micro Tesla, or probably few hundred micro Teslas, or fraction of a milli Tesla. So typical values are of that order. Okay. Anyway, so this is basically the difference between a magnet, permanent magnet, and an electromagnet. And then we're going to explore the effects of magnetism on moving charges. It's a very important behavior, because without it, we would not be here to talk about it. None of us would be here. Not a single one of us would be here. And that has to do with the charged particle that leave mainly the sun and actually come from also the cosmic radiation, and they hit the upper atmosphere. Because the Earth is actually a big magnet, those charges, they spiral because of this force, the force that is due to an electromagnetic field, and they fall either in the North Pole or the South Pole, hence the southern or the northern lights, basically. Okay. And then, because a wire carrying current actually is a bunch of charges moving along it, so it's the same behavior also can be expected on the charges on a wire. I mentioned a few times the Earth magnetic field, and there is a website actually by NOAA that you can go and look into the magnetic field in where you live, okay? And magnetic behavior is not exclusive to inert matter, but also to biological matter. So this is in a nutshell what we'll be covering in this chapter. So the term magnetism comes from the name Magnesia, a coastal district of ancient Thessaly, which is in Greece, actually, because there is a mountain in there where people noticed that, hey, if I take a rock from there, it attracts one another. So that's how basically magnetism was initially probably documented, but it existed in a lot of regions in the world, not just in Greece, okay? So these stones were called iodine stones, had the intriguing property of attracting pieces of iron. Magnets were first fashioned into compasses and used for navigation by the Chinese in the 12th century. Okay, so that is really the how the history of it when it came to magnetism. Because then it gave us a way for navigating during daytime. So during nighttime, you can rely on the stars if there are no clouds. But during daytime, now you can navigate knowing exactly where the north is. And all you have to do is stand and point to the other direction, and you have east-west. Okay. The electrostatic force that we discovered, if you guys remember, if I have a charge in here, Q, I'm going to give it Q, and charge Q. Well, we documented the force between it according to Coulomb. The force depends on these charges and also depends on the distance between them. For this one, for magnetism, you have to have a charge and you have to be moving, both. You cannot just have a charge and expect to play the game of magnetic force. No, you have to have a charge and the charge be moving. And then there you have magnetism. Okay. And the force is quite complicated a little bit. It involves something called the cross product. And the force is not in the direction between the particles. And it's not along the direction where they're moving. It's actually in a plane perpendicular to that, both of them, okay? So it's quite complicated. Now I use the word charge, a moving charge is magnetism. That is true. So what in the world is going on with neutrons? Okay? Neutrons have no charge, but they have magnetism. They have magnetic properties. They respond to the magnetic field, and actually they create a magnetic field too. Okay. So this is the condition to play this game. Except neutrons, they have a charge that is 0, and whether they're moving or not, actually they have to be moving because they are elementary particles. They have magnetic properties. As a matter of fact, the strongest magnets ever recorded are by neutron stars. Stars that are made uniquely of neutrons, okay? Stars that are so massive that their protons and their electrons basically merge together and form neutrons in addition to the existing neutrons, and the star basically becomes just neutrons every which way you go, okay? Of course, it has tremendous force of gravity, but that's not the only thing that the neutron star has. It has also tremendous amount of magnetic field. that can basically rip your atoms, destroy any matter next to it just because of the sheer strength of the magnetic field. So if a neutron star ventures close to Earth, it's going to wreak havoc on the Earth like nothing else because of the fact that it has tremendous magnetic field. So the question is, what's going on? Why neutrons have this peculiar behavior? They don't have a charge, and they play the game of magnetism. Anybody knows?
Not a clue.
Okay, that's fair. Listen, we can leave this toward the end, okay? So hold me to try to answer this question, okay? Because it's an important question. So yes, an electron moving can create a magnetic field and can be subject to a magnetic field. But a stationary electron, because it has Q, does not have V, cannot create a magnetic field. And if it's in presence of magnetic field has no bearing whatsoever on it. Same thing. Proton moving can create a magnetic field, or this can be subject to a magnetic field, basically the force. Neutron has no charge and can do the same things as far as magnetism is. You put it in an electric field, neutron has no clue whatsoever because it doesn't have a charge. Put it in a magnetic field, it's going to behave differently. It can create a magnetic field and actually also can respond to it, just like the other two, okay? Just like the other two. Okay, so let's continue this topic in here. So magnetic force between a pair of magnets, force of attraction or repulsion between a pair of magnets depends on which one of the magnets is held near the other. Behavior similar to electrical force, strength of interaction depends on the distance between the magnets. Obviously, if I take two magnets, I have been in the lab working with the lab assistant, and she swore to me that she saw that the North Pole was actually attracting a North Pole. I don't remember exactly if she said North Pole, or South Pole, but what she was really insisting in is that this, let me remove one of them to have the equal number. So this must be of a different poles, okay? Now, if I flip one of them, it's an attraction still. If I flip the other one, it's an attraction still. So what's going on in here? This is attraction. Now it's repulsion. Okay, I'm trying to push them, and they don't want to go close to one another, okay? So you have to be careful with this statement in here, because when it comes to magnetism, it's not as obvious as it is because it depends on the strength, okay? A magnet that is positive, I mean, by the way, positive and negative or north and south are just semantics, okay? That means they're different, that's all, okay? They're not the same, opposite to whatever they are, okay? So in here, I have two different magnetic charges, if you want to call them charges, of opposite sign, I mean, of similar sign. So if I try to push them to one another, they can't, they repel. Actually, I'm trying. So if I try very hard, and if I let go of it, it's going to flip in the opposite direction. Now, if I go to the opposite direction, same thing. So like charges, like magnetic charges repel, and like magnetic charges attract. That is true, okay? However, if one of them is stronger than the other, what it can do is it can reverse the polarity of the other one and cause it actually, if it was north, but strong north, and the other one was north, but a weak magnet, it can reverse the polarity of this magnet and make it behave like it's a south-north, so it's going to attract it to it, okay? This is an induced magnetic field in the other one. Now, if you remove that, the behavior will stick, okay? Will stick with it. So you have to be very careful in here, because there are ferromagnets and there is ferrimagnets. So the materials also, they come in different properties. There are a lot of properties of magnetic material when it comes to magnets. So it's not like straight cut shut street statement when it comes to, for example, charges. Okay. So magnetic poles, again, give rise to magnetic force, two types of interactions each, north pole and south pole, or north seeking pole and south seeking pole. Rule for magnetic force, forces between magnetic poles, like poles repel and opposite poles attract. So when you saw the demonstrations. If I have iron filings, and I do have them somewhere in here. No, that's not them. Here they are. Yeah, stop sharing. So these are called iron filings. Basically, they are tiny magnets and floating in here that you can see in here. And if I put them next to a magnet, they should exhibit, they should respond to the magnetic field by redistributing themselves. So I'm trying to bring a strong magnet in here because these magnets are actually weak a little bit. Okay, so right now, so I try to make it as uniform as possible. I probably should change cameras. Hold on. Okay, let's see here what kind of camera I have in here. Camera. Ah, poor lighting. So I'm going to put the magnet in here next to them. You can see already the orientations for them changed, okay? So the magnet is underneath. Again, they have no distribution. And as I bring them closer to the magnet, there is a distribution of the charges in here depending on the magnet. I don't know if you can see that or not. Maybe if I turn on the light in there. Hold on. Is this improved a little?
It's a little better, yeah.
Okay. So these are the iron filings far away from the magnet. Actually, they're trying to rearrange themselves, okay? If I bring the magnet next to them, you see the distribution in here starts to change. Now, if I move this magnet, they move with it actually. And this will give me the field lines. I don't know if you can see what looks like it's a hair-like structure right now. Let me turn this camera again, because this should stick no matter which camera can you, oops, I didn't need to turn it off. Okay, so this is basically how the structure is right now. If I remove this one, they will fall. If I bring it back in here, I have to actually come up with a random distribution. Otherwise they will, especially with this strong magnet. Okay, so these are the iron filings. Those are the field lines. So what you're looking at in the picture in here are actually the field lines. The field lines, so this iron filing will follow the field lines. So this in here from the North Pole, the field line leaves the North Pole and goes to the South Pole. So if you do the same experiment as I did before with this horseshoe, I should really see something similar to the other magnet, except now the field lines should follow, but they're super weak in here, okay? They're super weak. You cannot even, I mean, because this magnet is not as strong as, gravity will win over it. But if I remove them, they will also stop from working. Anyway, so this is demonstration basically of the field lines, and the iron filings, because they are magnetized, they will follow these field lines. So that's exactly what you were looking at earlier. So by convention, the direction is from North Pole to South Pole. This is basically the field lines, the magnetic field lines. Here is a picture of what I was talking about, the iron filings in here on a magnet. This is actually a clear material in here. And then if you sprinkle around it, this is how it looks like, okay? So these are the field lines in here. They leave the North Pole, and if you follow one of them, you're going to find it terminate in the South Pole, and North Pole, South Pole, which means that unlike the electric field, which is really comes from the positive charge and goes to infinity, this one's no matter what you do to it, it's going to come from the North Pole, and no matter how far it goes, it's going to terminate back in the South Pole. So the magnetic field actually circulates, goes around in circles, whereas the electric field actually flows like water, basically diverges from the region where you have it, where you started from. So again, this is the electronics picture of what's going on the atomic level. You have the spin, the individual spins of the electrons. Again, a lot of the electrons, their spins cancel, and that is due to a principle called Pauli principle. Okay, they cannot coexist in the same energy level unless something happens to them, where at the end the spins will be opposite to one another and they cancel each other. But the outer electrons, they can do that. They are basically individual electrons, so they don't cancel, so their spin is still a finite value on average for each atom. Now, in addition to that, the nucleus also has a spin, but as I was saying in the beginning, the proton is about 1800 times more massive than the electron. And because the actual property is not just the spin by itself, but it's actually inversely proportional to the mass, the electrons are the main players when it comes to magnetic force. Okay. Now, also, in addition to that, there is this orbital motion around the center of the atom. Okay. So that is. So the source of magnetism are electrons rotating around the atomic nucleus, electrons spinning around its internal axis, either A or B, or that's tiny bits of, I don't know. Okay. So both A and B. The denser the field lines, the stronger the magnetic field. That is by convention, actually. Again, as I was saying earlier in the introduction, different regions for, doesn't matter what the material is, have different orientation for their magnetic field in general. So nearest neighbors start to work together, and as if you have a current now. So basically, let me take an atom in here. Where is my pen? Here. So let me take a group of atoms next to one another in here, in this schematic. This is a region of space. If this electron can cause a current, effective current, basically moving counterclockwise, this one also counterclockwise, 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 all of these electrons in each and every one of these atoms is counterclockwise. This who is counterclockwise. If I look at the region where they meet, this is where these two atoms, they meet. This one is going this way and the other one is coming that way, so this region cancels out. And this region also cancels out because for this atom, the electron is going this way, the other atom also is going this way, so in this region they cancel out. So wherever the electrons, basically where the atoms intersect, they cancel. The inner ones, they cancel completely. They cancel with this one because it's moving this way, this electron is moving this way, this electron moving up, this one is down. So the inner ones, they cancel no matter which region you have. Overall, what you have in here, as if you have a current now going around the outer edges of this region, resulting for what looks like a current, okay? This is an effective current, not a real one. So which way that current flows, that is the magnetization for that region. The other one could have a different magnetization, this one a different magnetization, and so on and so forth. On average, because of the random thermal agitation, they cancel out. All the regions are completely in different random fashion, except some materials, like I said in the intro, can help one another retain their magnetism when the external agent that caused it is lifted. And those are what is called the self-consistent solution. Now, if you raise the temperature again, there is a point where you lose magnetism. I was in middle school, actually, and I had magnets like this one playing with it. Actually, I have only one magnet playing with it. And it was a very cold night, and we had the heater. It was an electrical heater running. So I put my magnet on a spoon, and I brought it next to the heater. after it cooled down, it lost all of its magnetism. I was devastated. I went to my science teacher, explained to him, he told me you reach Curie temperature. So when you reach Curie temperature, the material loses its magnetism because, again, that random motion will cause that the material in this case will not be magnetized anymore. You have to really magnetize it. Okay, you have to take it and put it in a permanent magnet to, again, and then the different domains will retain their magnetization. It is these domains actually the ones that are used for data storage, because if I somehow magnetize a material in different domains, for example, this one up, this one down, this one down, this one up, this one up, and so on and so forth. Each region can be allocated basically a code and becomes part of a binary code. So that is basically how data is stored. So converting these domains into, for magnetic materials, into binary code, okay? So if it's up, for example, it's 1. If it's down, it's 0. So now I have this number in here in a binary code, which is 11100. So if you're familiar with the binary code, this is a number actually. I have how many? 1, 2, 3, 4, 5. So it's 2 to the power 5 plus 2 to the power 4 plus 2 to the power 3 plus 0 plus 0. No, that's 2 to the power. 0 times 2 to the power 1 and 0 times 2 to the power 0. So this is what 2 to the power, that's 8, 16, and 32. So this is a number plus 2 zeros. Anyway, outside, forget about this. But it can be used as part of data storage. And that's why most, at least before the optical devices now that are used, like for example, flash cards and flash stuff that we have nowadays, or the new hard drives, the old hard drives were actually magnetic materials. They were using the properties of the magnetic materials to store data and retrieve data. And data storage was using magnetic materials. Data erasure also was a big topic that the military paid a top money for it, especially when you're trying to keep the data safe from being read. Because all you have to do is just take the hard drive and basically reverse look at the configuration of the domains. Even though you deleted it, you can go back in the history and find exactly what was in the information in it. There's a lot of stuff in here in this topic, okay? Fascinating stuff. So again, there are two kinds of magnets. There is a permanent magnets and there is electromagnets. Okay, electromagnets are temporary magnets. And as I was describing in the beginning in here, if you cut a magnet in two, so basically what you end up is, because the magnetization is, if this entire thing is magnetized, then all you did was actually cut it somewhere in the middle where you kept the orientation in the same direction. So you still have north and south. Electricity can produce magnetism. That's exactly the demo that I was to show you guys. That's how electrical magnets work. I'm going to do it in the context of a motor. So this is what I have in here. Let me stop sharing the screen and explain to you what I have. I probably use the other camera still better. So let me switch cameras. Okay. So what I have in here, so it's not focusing. Okay, so what I have in here, I have if you can see in here, there are wires in here that are, it's called the coils actually, that are turning on this material. This has no magnetic properties whatsoever, this material in here, but this ones do, okay? So in this case, I mean, they have a permeability in this case. So they have some magnetic properties, but not that of a permanent magnet. So what I have in here, I have 3 batteries. Each and every one of them is actually 1.5 volt. So what I did in this case is I connected this battery, from the negative side to the positive side of the other one, and the negative side of this battery to the power source, and the positive side of this one to the negative of this one, and this one now is a battery. So effectively, I should have 3 batteries in series from one another. So basically I have 1.5 and I have a 1.5 and I have a 1.5 for a total of about 4.5, 4.5 basically volts. So that should create strong enough current for me to see that this is working. So I need to test to make sure that I have really a 4.5. This is a voltmeter. I mean, it's behaving as a voltmeter right now. So I'm going to turn it on. Right now I turned it on to the voltmeter. I should expect to see a reading of about 4 volts, okay, between the last end of the of this battery. So I need to have the proper end of it. Okay, and the first one. And it's giving me 4.8 if you guys can see the number. So it should be about 4.5. And typically each and every one of them is about basically, so right now I have a 0 volt in the reading. So again, if I put this one in the red, and this one is in the first battery, I should have about 4.8 volts. I mean, I'm expecting 4.5 and that's fine. So it's good. So I have, that's important because I need that property, I need that magnet to have that, I mean, I need the battery to have that much current to make sure that I have enough current running through this one. I connected already the negative from this battery to this battery, which is connected from this one to this one via this wire. And this wire now is connected to this battery, and this battery now needs to be connected to the circuit to close it. If I do it, then I should see that this becomes a magnet, and there is already a magnet, and the 2 magnets starts to basically attract and repel one another, and you should see that this one starts to move. Do you think it's going to work or not? At least so to a point that you can see it.
Yes.
Okay. Anybody else?
Yeah.
Okay, so let's see if it's going to work. So definitely, it's a very strong magnet, okay? I tried it actually with the 1.5 volt and it still worked, but not as good as the, so this is actually a motor now because you can use it to grind coffee if you like, okay? You see the spark? Do you see the spark that come in when I turn on? And this point in here. No. It does not look. Did you guys notice it or not? That's part of the transient behavior. Sorry, did you say?
I saw it.
Okay, that's part of the transient behavior. Okay, anyway, so let me go back into the other camera and continue. So electricity produces magnetism, and that is the bottom line of this experiment actually. This is an electromagnet because now I have 2 magnets interacting with one another, pulling and repelling each other. And that's how actually motors work too. And it's the same principle. We can use it actually to reverse engineering stuff and create currents. Okay. So let me share the screen in here, share. So this is the whole point in here of this experiment, which way it's going to go depending on the current. If your thumb is where the current is, the magnet will curl around your thumb according to how the palm goes. It has to be the right hand. You cannot use your left hand. So if you're left-handed, you're out of luck. You really have to use your right hand. So if the current is your thumb, going in your thumb, the rest of your palm is how the magnetic field curves around the current. So that is basically how this phenomenon is. To go back into this point in here that I was demoing in here, the current actually was going in and out, okay? Was going through these wires in here, okay? And these wires were creating a magnetic field in this direction, which was interacting with these 2 permanent magnets. So that is basically how this thing is working in here. And because of this brush, I don't know if you see it or not, there is a brush actually in here, next to my finger, in the middle, right in between these 2. It's metallic, like that is actually where the current is actually changing. You could see it probably from the top in here. This is the one. It's very sensitive. If I move it, I probably will break it. So I don't want to do that. This is why engineers do stuff that physicists can't. So again, this is the iron filings, and that really reiterates the point I was saying, that the magnetic field circulates around the current. The current is in and out of it's on this wire. So it circulates in here. Again, it's circulating around where the current is. So that's what you see in here. It looks like I have two regions in here. In here, it's trying to circulate, but the minute it circulates, it finds another one, so it comes out in here. And this is exactly the behavior of that device, and it's actually used in a lot of electronics too. So if you open any of your electronics, you will see that we have the same coils actually that are used usually near the power supply, like in here, near where I am pointing in here. So there is one in here, there is another one in here, and this is part of a device that I really forgot what it used to do, that it destroyed. So there is one in here too. There is one in here. So you find this kind of devices. They're used as transformers most of the times in electronics, but also they use because of their induction properties. So sometimes you really want to have a signal and you want it to vary and so on and so forth. So they're used, as you can clearly see, this is part of an antenna somewhere that is connected to a hookup. That's why you need this one's a part of a signal in here, telecommunications, okay? So again, these are capacitors. There are different stuff in here. And this is your HDMI cord, the normal HDMI cord, and this is your This is your HDMI, this is your USB cord, okay? So this is stuff that you can use everywhere, okay? In electronics. So this is the device I was talking about that is used in electronics. It's this one, called an inductor actually, this one in this picture, the third one in here. Again, electromagnets are so powerful that they are used actually in levitating trains. So levitation in here. So they are actually very powerful. And the functioning of the whole train actually is being propelled and pushed by magnets. So a current carrying coil of wire is an electromagnet. The strength of an electromagnet is increased by increasing the current in the coils or increasing the number of turns. That's why you see so many of them, okay? Because one of them, two of them, now you have many of them. Or having a piece of iron in the coil. That is increase the magnetic flux inside. So what you do, you put an iron in between, and that becomes, like in this case in here, I don't know if you noticed or not, there is actually inside the coil, there is this part of this piece in here that increase the flux, which is really what matters at the end of the day, the magnetic flux. And again, for magnetic permanent magnets, its magnetic domains in the iron core are induced into aligning themselves, adding to the field. So, oh, I'm sorry, that's the in here, okay? Superconductivity also has fascinating stuff with the magnets because magnetism cannot penetrate superconducting materials and cause the material actually to levitate. So that's... So a charge inside a magnetic field will experience basically the effects of the magnetic field, okay? So this is how it's there. So let's say, for example, the magnet is in a region that is going into the screen. So think with me for a second that you have a big magnet where the north is going this way to the screen and the south is on the other side of the screen, okay? So the north is this way, the south is on the other side of the screen. And now you have a charged particle that comes in. When the charged particle in here that comes in, it's going to deflect and it's going to go in a circle and come back, okay? So that's really what a magnetic field on a charge is. So it makes it go in a circle. Magnetic field does not do work. Magnetic field only bend the motion of the charge, makes it move this way. So if I have the magnetic field inward, the particle is moving upward, so it's going to bend this one. This is a positive charge. If it were a negative charge, actually it can be used, it can go the other way. It has a lot of applications, this thing in here. One of its applications, you can use it as mass mass spectrometer, sorry, to distinguish between the different isotopes of a given element. Let's say, for example, you have an element in here that comes in with two different isotopes, one more massive than the other. Since they are isotopes of the same material, they have the same charge. So Q is the same. And provided you run them through something called the velocity selector, so they have the same velocity. So where one would land and the other one would land depend only on their mass. So now you have effectively separated the materials into two different ones. So this is why it's called mass spectrometer. Because you can take ions and separate them, depending them in different isotopes and separate them depending only on their masses, because that's how isotopes are different. They differ only from their masses. You can use it actually as a nuclear accelerator, and the first nuclear accelerator used this technique called the cyclotron to accelerate particles, because the minute they merge from the other side, since they are charged particles, you can actually apply an electric field on them and accelerate them. Once they go in the second region, just put another permanent magnet in the same direction and they will bend backward. So in here, when they emerge from here, just flip the polarity. You don't have to increase. You don't have to pay more for the power company. Just keep the same voltage. Now they're going to accelerate more. And you kept this doing this back and forth, back and forth, and back and forth. And all of a sudden, you have acceleration of particles, tremendous speeds, without a lot of cost. Okay? So there is these things in here that are properties of how charges interact with the wires, with the magnets, that are useful for a lot of applications. Actually, it's used also in the old cathodic TVs, in the old, basically, not the LCD screens, in the old regular CRT screens, okay? And that is basically you have a charge, which is an electron in this case, coming, and depending on depending on the signal that came in, the voltage and the current, that causes the voltage, and also the magnet that is forming in there depends only on the signal that sent it. So now the electron can land on a specific point on the screen depending on that. And because screens, they were fitted with fluorescent materials, so depending on the intensity with which it hits, it's going to produce a certain impact. If it was a monochromatic screen, basically CRT screen that is all green or all yellow, in that case, it's going to produce a dot here and there, depending on the signal, and at the end, it's going to produce an image or text or whatever you were doing with it. Nowadays, it uses different technology called LCDs. Anyway, the same effect also happens with wires, because wires are just a bunch of charges moving through it, and they bend in the same fashion. We're doing on time. So again, the bending depends on which way the current is flowing, that's all. Electric meters also use, because now if the strength of the current is very high, the needle will bend so much. If the current is slow, because they will create a strong magnetic field, which causes this needle to move very far away. If the current is weak, then the needle would not move as much. So this is actually, you can be used as a useful device to measure how much current is flowing in here. All you need is just coil the wires in a coil like this one and pull them out. So if there is no current, the needle does not go one way or the other. If the current is flowing weakly, so the needle will probably move this way. The current goes stronger, it moves this way. All you have to do is place a dial in here of 0, here, for example, of 1, here is of 2, and so on and so forth. Now, if the current is flowing in the opposite direction instead, the needle will move in the opposite direction, and that's it. So this will become -1, and so on and so forth, -2, and so on and so forth. So that's why it's used in the multimeter devices like this one in here, the vector port, or this one. This is actually a voltmeter or an ammeter. So those are devices that are used the same technology here I was talking about. And like the one I was showing you before, this one is actually digital, okay? Actually more precise, I like that one better. And this is the motor I was demoing earlier. And this is the brush that I was talking about earlier. It's in here, okay? This is the brush I was talking about in here. I really don't want to touch it. Let me see if I can get this to back in here. It's this one. That is the brush. That's the same one in there. It's very important. It has to have a gap in it. Otherwise, the motion will get stuck. It's not going to move anywhere. That's how engineers get paid for, doing these things, creating stuff like that one. Okay, the Earth is a big magnet, and that's because of the heat that it generated in its core, and that heat will cause the nickel and the iron basically inside of it to move at super high temperatures because it's ionized. So it has a current, and that current actually is the same thing that causes magnetism in a permanent magnet, or even in an electromagnet. So the Earth is a huge magnetic magnet. And let me see if I can find Noah. You stop sharing the screen to show you something very nice. Share this screen. So let's say, for example, you want to know how much magnetic field is in your region, okay? Let's say, for example, it's 2001 3rd Street, Norco, California. What is the zip code? 92860 for the college? Does everybody know? Yes. I think it gave me the latitude and the longitude. I need those ones in here. So we are north and we are west of the time zone, and the model, and then so this is NOAA's website. It gives you the magnetic field of where you are, and sometimes you need that information, especially if you're doing experiments and you want to learn about what's going on and things like that. So it gave me here. What is this? It gave me here. No, I don't want the north and the south, how they move. I want the strength of the magnetic field. No, not the magnetic field. That's the one. I'm sorry. Okay, that's the one I need. Okay. Okay. Let's say, for example, it's about what? How many feet is that area there? Probably 100 feet above the sea level. I'm just throwing the numbers in there. This is the one I want. I want the magnetic field. You see here, so much information you can take from their website. Now it's giving me the magnetic field. The total magnetic field on the 29th of April of the year 2021 is 46,000 nanoteslas. Nanotesla is 10 to the negative 9. So it's 46 microteslas. So that is the point I was saying earlier. So the magnetic field is not that strong. Is everybody, am I sharing the screen or not?
Yeah, you are. We see it.
Okay, very good, because I don't see the point being in here is that this is a useful website where you can find the magnetic field in your region. So let's say, for example, you're doing stuff or experiments or trying to find out, curious or something. This is actually a very useful website where you can get a lot of data in here. All you have to do is just put your address. I put the college's address in here. That's not where I live, okay? So that's basically, I don't know exactly the elevation, which I can Google and find out if you're curious enough. And then you're above the sea level. And once you have that, it gives you the strength of the magnetic field. This is just to give you an idea into how strong the magnetic field is. So stop the share. What I want you to do is have fun with this website, which I'm going to share with you guys. Okay, 640 feet. Thank you very much. So probably I should correct that one. Okay, here is the link for the NOAA's website. If you're not sure, just go to the internet, to Google or Bing or whatever your search engine, and look for NOAA. That's NOAAA, NOAA, and look for their magnetic field calculator. Go there. Make sure you are in the magnetic field, though. Don't go into, like, I don't know what I was doing earlier at the beginning. Okay, declination. No, I don't want the declination. It's important also to see that too, in case you're trying to do some. And then from there, you're going to put your address, and you're going to tell us what's the strength of the magnetic field in your area. Okay, it's the total value that you see in there. It's going to be in NT. N stands for nano, and T stands for Tesla. And let's see who's got the strongest magnetic field in his or her region. Okay, it's not a context. Okay, so don't invent numbers. Okay, it's just to see if there is any fluctuations into where you guys live roughly. It should be very close from one another, but I want to see. I'm kind of curious, trying to find out exactly which one has the strongest magnet. And this is due to Earth, of course. Okay, the magnetic field turned out to be a very useful thing for us on Earth, because it can protect the Earth from, as I mentioned before, from the cosmic rays and fast-moving charged particles. If it were not there, we would not be here actually to talk about it. So the fact that we have a magnetic field on Earth protected life on Earth, because otherwise these supercharged particles would decimate life on Earth, every form of it. So this is the aurora borealis or aurora australis. These are the charged particles coming down because they are spiraling and going down to the Earth, actually. So that's good that we have a magnetic field on Earth. Otherwise, we wouldn't be able to talk about this one. Apparently, magnetism is used by living organisms also for navigation and other things. And for some reason, they're sensitive to the direction of the magnetic field, and you can mess with them, okay? If you change the value, because they are very sensitive to the values of the magnetic field, and basically they find their way to where they need to go. Okay, so this is your chapter in a nutshell. And please don't forget this assignment. I'm kind of very excited about it, to see your data, and we will see what that is, okay? Sounds good?
Oh, that's the discussion point.
Yes.
Right, I was looking mine up.
Yes.
Okay, so you have the link in there. If for some reason you don't find it, please let me know. I will send it to you again. If not, you can actually Google NOAA for finding the magnetic field in your region. We use this one actually for the lab, because sometimes when we measure the magnetic field in the lab, we find errors in the measurements. So what I ask my students to do to see if they can find any corrections to their lab, just by basically, because if you send so many amps, and you do the calculation, you're expecting a value for the magnetic field, and that value for the magnetic field is going to impact another measurement you're supposed to do for E over m, for example, for the charge of the electron versus the mass of the electron. But then you find a big error, and you say, okay, where did I go wrong? Okay, so in this case, probably the magnetic field of the Earth played a role. The reason why it plays a role in where you are is because the magnets that we're dealing, the currents we're dealing with them with the lab are not too strong. So we really don't have a lot of strong magnetic field. So when we make that correction, it improves the error a little. So I use this website actually for my students when we were live and doing labs. Okay, good. So I'm going to stop the recording.